As you rest peacefully tonight, imagine holding in your hand something so ordinary you rarely give it a second thought. A single raindrop, perhaps caught on a leaf or resting on a window pane. This simple sphere of water, no larger than a few millimeters across, contains within it an entire universe of physics, chemistry, and even life, demonstrating that the most commonplace objects around us harbor extraordinary complexity when we take the time to look closely. Tonight, as you drift towards sleep, you'll journey into the hidden world inside a raindrop, discovering how it forms miles above Earth's surface around microscopic dust particles, how it grows by collecting water vapor and colliding with other droplets, how surface tension sculpts it into its characteristic shape, how it contains dissolved gases and minerals that tell stories of its journey through the atmosphere, and how it may even carry living microorganisms traveling through the sky in this tiny vessel of liquid. A single raindrop represents the culmination of the water cycle, that grand circulation of H2O between ocean, atmosphere, and land that has been operating since Earth first cooled enough for liquid water to exist on its surface billions of years ago. The water molecules in tonight's rain were once part of ancient seas, were breathed by dinosaurs, flowed through the veins of prehistoric forests, fell as snow on Ice Age glaciers, and cycled through countless organisms before evaporating back into the atmosphere to eventually condense into the drops that will fall tonight. Each raindrop begins its life not as liquid water, but as water vapor, invisible gas molecules floating freely in the atmosphere, waiting for the right conditions to transform back into liquid. This transformation requires more than just cold temperatures. It needs something for water molecules to gather around, a nucleus that provides a surface where the first molecules can stick and begin the process of droplet formation. These condensation nuclei are everywhere in the atmosphere. Microscopic particles of dust lifted from deserts, salt crystals from ocean spray, smoke from wildfires and industrial processes, pollen from plants, even bacteria and fungal spores floating through the air. Without these tiny particles, raindrops couldn't form, and Earth would have far fewer clouds despite having abundant water vapor in the atmosphere. The raindrop falling tonight owes its existence to one of these microscopic particles that served as its seed. As water vapor molecules collide with a condensation nucleus and stick to it, a tiny droplet begins to grow, starting smaller than the width of a human hair. In the cold upper atmosphere where clouds form, this droplet gradually accumulates more water molecules, growing larger as it rises and falls within the cloud in air currents, sometimes freezing and melting multiple times, colliding and merging with other droplets, until finally it becomes large and heavy enough to overcome air resistance and fall toward Earth as a raindrop you might feel landing on your skin. The journey from cloud to ground transforms the raindrop, adding complexity to its simple appearance. As it falls through different atmospheric layers, it dissolves gases, oxygen, nitrogen, carbon dioxide, that change its chemistry. It may pick up pollutants from industrial emissions or natural compounds from biological activity in the air. By the time it reaches the ground, a raindrop has become a tiny time capsule, recording information about atmospheric conditions, air quality, and the vertical structure of the lower atmosphere through which it descended. The shape of a falling raindrop contradicts the popular teardrop image we often see in stylized drawings. Small raindrops, less than about 1 millimeter in diameter, are nearly perfect spheres, held in this shape by surface tension, the cohesive force between water molecules that makes water behave as if it has an elastic skin. Larger raindrops become flattened on the bottom by air resistance as they fall, taking on a shape more like a hamburger bun than a teardrop. The very largest raindrops, approaching 5 or 6 millimeters in diameter, become unstable and break apart into smaller drops, establishing an upper limit on raindrop size, determined by the physics of surface tension and air resistance. Inside this tiny sphere of water, molecules are in constant motion, vibrating, rotating, and forming temporary hydrogen bonds with neighboring molecules before breaking apart and forming new bonds. A dynamic molecular dance that occurs trillions of times per second. This molecular activity gives water its unique properties: the ability to dissolve a wide range of substances, the capacity to store heat, the expansion when freezing that makes ice float, and the surface tension that holds the raindrop together as it falls. As you prepare to explore the universe inside a raindrop tonight, rest in the knowledge that you are about to discover how much complexity exists in the simplest things. How a single drop of rain connects to global cycles, ancient history, atmospheric physics, chemistry, and even living organisms. The raindrop falling outside your window represents not just water, but a tiny world unto itself, a microscopic universe that reflects the larger patterns and processes that shape our planet and make life possible. The birth in the clouds. How raindrops form. Journey now into the clouds where raindrops begin their existence, discovering the delicate physics and chemistry that transforms invisible water vapor into the visible drops that eventually fall as rain. A process that requires precise conditions of temperature, pressure, and the presence of microscopic particles that serve as gathering points for water molecules. The formation of a raindrop begins with a process called nucleation, the initial gathering of water molecules around a condensation nucleus floating in the atmosphere. This nucleus might be a particle of mineral dust blown from a desert, a crystal of salt left behind when ocean spray evaporates, a microscopic fragment of ash from a distant wildfire, or even a bacterium carried aloft by winds. Without these particles, water vapor would remain as invisible gas even at temperatures well below the normal condensation point, demonstrating that phase transitions in nature often require a little help to get started. Once water molecules begin adhering to a condensation nucleus, the tiny droplet grows through a process called accretion. Additional water vapor molecules in the surrounding air collide with the droplet and stick to it, adding their mass to the growing sphere. This growth occurs molecule by molecule, a slow accumulation that gradually increases the droplet size from microscopic dimensions to the visible cloud droplets that scatter sunlight and make clouds appear white. But cloud droplets are not yet raindrops. A typical cloud droplet measures only about 10 to 20 micrometers in diameter, roughly 1/5 the thickness of a human hair. These tiny droplets are so small and light that even slight upward air currents keep them suspended indefinitely, creating the clouds that float peacefully through the sky without immediately precipitating. For a cloud droplet to become a raindrop large enough to fall to Earth, it must grow to at least 100 times its initial diameter, increasing its volume a millionfold. Two main processes drive this dramatic growth from cloud droplet to raindrop. The first, called collision coalescence, occurs in warm clouds where temperatures remain above freezing. Cloud droplets of different sizes fall through the cloud at different speeds. Larger droplets fall faster and collide with smaller droplets in their path, merging upon contact and growing larger with each collision. This snowball effect accelerates as droplets grow, allowing them to sweep up even more droplets and eventually become large enough to fall as rain. The second process, called the ice crystal process, or Bergeron process, dominates in cold clouds where temperatures fall below freezing. At these temperatures, clouds contain a mixture of supercooled water droplets, liquid water that remains unfrozen despite being colder than the normal freezing point, and ice crystals. Because the saturation vapor pressure over ice is lower than over liquid water, water molecules evaporate from the supercooled droplets and deposit directly onto the ice crystals, causing the ice to grow at the expense of the liquid droplets. These ice crystals grow into snowflakes that may eventually become large and heavy enough to fall from the cloud. As they descend and pass through warmer layers of the atmosphere, they melt into raindrops, often retaining some of the structure from their crystalline phase in the form of slightly irregular shapes or multiple centers within a single drop. The rain falling on a warm day may have begun its life as a snowflake miles above your head, transformed by the temperature gradient of the lower atmosphere. Inside developing clouds, powerful updrafts can carry growing droplets and ice crystals upward repeatedly, allowing them to cycle through multiple rounds of growth before finally becoming heavy enough to overcome the updraft and fall toward Earth. In severe thunderstorms, these updrafts can be so strong that they loft droplets and ice high into the cloud multiple times, allowing them to accumulate layers of ice and grow into hailstones, frozen raindrops that have experienced an extreme version of the normal raindrop formation process. The size distribution of raindrops in any rainfall event tells a story about cloud conditions and droplet growth processes. Light drizzle consists primarily of small droplets, around 0.5 millimeters in diameter, indicating weak updrafts and limited collision coalescence. Moderate rain contains droplets ranging from 1 to 3 millimeters, suggesting more vigorous cloud processes. Heavy rain and thunderstorms produce the largest droplets, 3 to 5 millimeters across, generated by strong updrafts and efficient collision coalescence in tall, active clouds. The moment when a droplet transitions from cloud droplet to falling raindrop represents a phase transition, not in state of matter, but in behavior. The point where gravity overcomes air resistance and suspension mechanisms, where the drop begins its inevitable journey toward Earth's surface. This transition occurs when droplets reach roughly 100 micrometers in diameter, large enough that even modest updrafts can no longer keep them aloft indefinitely. As raindrops fall through the lower atmosphere, they continue to evolve. Some evaporate partially if they fall through dry air layers, shrinking as they descend. Others continue growing by sweeping up smaller droplets in their path. The fastest falling droplets may overtake slower ones and merge, creating larger raindrops from the collision. This dynamic evolution means that the raindrop hitting your skin has a complex history written into its size shape, and internal composition. As you rest peacefully tonight, imagine clouds overhead filled with billions of tiny droplets and ice crystals, each one growing according to the same physical principles, competing for water vapor, colliding and merging, rising and falling in air currents, gradually transforming from microscopic particles into the raindrops that will eventually fall, carrying with them information about cloud conditions and atmospheric processes encoded in their size, composition, and temperature. The architecture of water, molecular structure and behavior. Descend now into the molecular realm within a raindrop, discovering how water molecules organize themselves through hydrogen bonds, how these bonds create water's unique properties, and how the arrangement of just 3 atoms, 2 hydrogen and 1 oxygen, produces a substance so extraordinary that it makes life possible and shapes Earth's surface, atmosphere, and climate. A water molecule consists of 1 oxygen atom bonded to 2 hydrogen atoms in a bent shape, with the oxygen sitting at the vertex of an angle measuring about 104.5 degrees. This geometry is not arbitrary, but emerges from the quantum mechanical arrangement of electrons around the oxygen atom, creating a molecular architecture that determines all of water's remarkable properties. The oxygen atom, with its higher electronegativity, pulls the shared electrons in the OH bonds slightly toward itself, creating a molecule with an uneven distribution of electrical charge. The oxygen end becomes slightly negative, while the hydrogen ends become slightly positive, making water a polar molecule, one with positive and negative poles like a tiny magnet, though electrical rather than magnetic in nature. This polarity allows water molecules to form hydrogen bonds with their neighbors, weak attractive forces, where the slightly positive hydrogen of one molecule is attracted to the slightly negative oxygen of another. Each water molecule can form up to 4 hydrogen bonds simultaneously, creating a dynamic network where molecules constantly form bonds, break them, and form new bonds in patterns that shift trillions of times per second. Inside a raindrop at room temperature, the average water molecule participates in about 3.4 hydrogen bonds at any given instant, creating a loose but interconnected structure that gives liquid water its unique properties. These bonds are strong enough to hold water together as a cohesive liquid, but weak enough that molecules can slide past one another, allowing water to flow, take the shape of its container, and dissolve a remarkable variety of substances. The hydrogen bonding network creates water's high surface tension, the property that allows the raindrop to hold together as it falls through air. Surface tension acts like an elastic skin on the water's surface, created by water molecules at the boundary pulling inward on one another more strongly than they pull on the air molecules outside. This inward pull minimizes the surface area of the drop, explaining why small raindrops form nearly perfect spheres. The sphere is the 3-dimensional shape with the minimum surface area for a given volume. Water's hydrogen bonds also give it an extraordinarily high heat capacity, the amount of energy needed to raise its temperature. Breaking hydrogen bonds requires energy, so heating water involves not just increasing molecular motion, but also breaking bonds, making water resistant to temperature changes. This high heat capacity makes water an excellent thermal buffer, stabilizing temperatures in lakes, oceans, and even inside living cells, protecting biological processes from rapid temperature fluctuations. The same hydrogen bonding creates water's unusually high boiling point. At atmospheric pressure, water remains liquid up to 100 degrees Celsius, 212 degrees Fahrenheit, far higher than would be expected for a molecule of its small size. Without hydrogen bonding, water would boil at about minus 80 degrees Celsius, minus 112 degrees Fahrenheit, making liquid water impossible at Earth's surface temperatures and eliminating the possibility of water-based life. Water molecules in a raindrop are constantly rotating, vibrating, and moving from place to place within the drop, creating a dynamic molecular environment where nothing is static. At room temperature, an individual water molecule moves at speeds of about 1,300 miles per hour, though it travels only microscopic distances before colliding with neighbors, bouncing in random directions in a process called Brownian motion. This constant molecular movement gives water its liquid properties and enables the diffusion of dissolved substances throughout the drop. The purity of a raindrop varies depending on where it forms and what it encounters during its fall. Distilled water would be pure H2O, but no raindrop achieves this purity. Every drop contains dissolved gases absorbed from the atmosphere, primarily nitrogen, oxygen, and carbon dioxide. These dissolved gases don't just float freely, but interact with water molecules through various mechanisms. Carbon dioxide, for instance, reacts with water to form carbonic acid, H2CO3, making even pure rainwater slightly acidic, with a pH around 5.6. Additional substances dissolved in raindrops include ions from sea salt, sodium, chloride, magnesium, sulfate, carried inland by winds after being lofted into the atmosphere when ocean waves break. Raindrops falling over continents may contain mineral particles dissolved from dust, sulfur and nitrogen compounds from natural and human sources, and organic compounds from vegetation and soil. Each raindrop becomes a tiny solution, carrying a chemical signature of its journey through the atmosphere. The isotopic composition of water molecules in a raindrop provides information about where the water originally evaporated and what processes it experienced. Water molecules come in different isotopic varieties. Most contain ordinary hydrogen and oxygen-16, but some contain deuterium-heavy hydrogen or oxygen-18, heavier isotopes that behave slightly differently during evaporation and condensation. The ratio of these isotopes in rainwater reveals the temperature at which the water evaporated, how many condensation cycles it experienced, and even how far it traveled from its source. As you rest tonight, imagine the intricate molecular dance occurring inside every raindrop. Billions of water molecules forming and breaking hydrogen bonds, rotating and vibrating in constant motion, surrounding dissolved gases and ions, creating through their collective behavior the unique substance that covers most of Earth's surface, fills your cells, and makes the existence of life as we know it possible. Living passengers. Biology in the atmosphere. Discover now the surprising inhabitants of raindrops, living organisms that travel through the atmosphere inside these tiny vessels, from bacteria that can influence cloud formation to fungal spores that disperse across continents, revealing that the sky above you is not empty air, but a living aerial ecosystem where microscopic life flourishes in unexpected ways. Bacteria are abundant in the atmosphere, with concentrations sometimes reaching thousands of cells per cubic meter of air. These airborne microbes are not dead particles, but often living organisms, capable of metabolism and reproduction, traveling through the air and occasionally being swept into forming raindrops, where they may serve as condensation nuclei around which droplets initially form. A particular group of bacteria called ice-nucleating bacteria possess specialized proteins on their cell surfaces that organize water molecules into ice crystal structures, even at temperatures warmer than water would normally freeze. These bacteria, including species like Pseudomonas syringae, are remarkably effective at promoting ice formation in clouds, potentially influencing precipitation patterns. Some scientists estimate that biological particles may serve as ice nuclei for up to 30% of precipitation in certain regions, demonstrating that living organisms don't just respond to weather, they help create it. The relationship between ice-nucleating bacteria and precipitation may represent a sophisticated evolutionary strategy. By promoting ice crystal formation in clouds, these bacteria may enhance their own dispersal through precipitation, allowing them to travel long distances and land in new environments. When rain or snow carries them back to Earth's surface, they return to plant surfaces, soil, or water bodies, where they can resume active growth, having used clouds and precipitation as a dispersal mechanism. Fungal spores are even more abundant than bacteria in the atmosphere, with some estimates suggesting that several 100 million fungal spores pass over every square kilometer of Earth's surface every day. These spores, produced by fungi for reproduction and dispersal, are so small and light that they can remain airborne for extended periods, traveling vast distances before eventually being washed out of the atmosphere by rainfall or snow. Inside a raindrop falling through the lower atmosphere, these fungal spores and bacteria exist suspended in the water, sometimes metabolizing dissolved organic compounds and gases, occasionally dividing and reproducing even during their brief aerial journey. The raindrop becomes a temporary aquatic microenvironment, a microscopic ecosystem where biological and chemical processes occur during the minutes or hours of the drop's fall from cloud to ground. Pollen grains, much larger than bacteria or fungal spores, also travel through the atmosphere and may occasionally be incorporated into raindrops. During spring and summer, pollen concentrations in the atmosphere can be enormous, with plants releasing these genetic packages to disperse on winds. When rain washes pollen from the air, each raindrop may contain multiple pollen grains, making precipitation a cleansing mechanism that removes biological particles from the atmosphere and deposits them on Earth's surface. Some researchers have discovered that organic compounds released by plants, trees, and phytoplankton in the ocean can serve as condensation nuclei, promoting cloud droplet formation. Isoprene and terpenes released by forests, for instance, can be oxidized in the atmosphere to form small particles that serve as seeds for water vapor condensation. This suggests a feedback loop where living organisms influence cloud formation, which affects precipitation patterns, which in turn affects the distribution and survival of those same organisms. The concentration of microorganisms in rainwater varies dramatically depending on local conditions and weather patterns. Light rain, falling after a dry period, often contains high concentrations of microbes because it washes out biological particles that have accumulated in the atmosphere. Heavy rain falling from tall clouds may contain fewer microbes because it falls quickly, spending less time sweeping through the lower atmosphere, where biological particles are most concentrated. Microbes in raindrops may even influence human health through their impact on air quality and respiratory illness transmission. Some airborne bacteria and fungi can cause allergic reactions or respiratory infections when inhaled. Rain cleanses the atmosphere of these particles, potentially improving air quality for hours or days after a rainfall event. The fresh smell of rain, called petrichor, comes partially from organic compounds released by soil bacteria when raindrops strike the ground, demonstrating another connection between precipitation and microbial activity. The study of airborne microorganisms, sometimes called aerobiology or bioaerosol science, reveals that the atmosphere functions as a vast ecological habitat, supporting diverse microbial communities. These communities vary with altitude, season, location, and weather conditions, creating an aerial ecosystem as complex and dynamic as more familiar terrestrial and aquatic ecosystems. Climate change may be affecting atmospheric microbial communities in ways scientists are only beginning to understand. Changes in temperature, precipitation patterns, and atmospheric circulation could alter the distribution, abundance, and activity of airborne microorganisms, potentially affecting cloud formation, precipitation chemistry, and the dispersal of plant pathogens, beneficial bacteria, and decomposer organisms. As you drift toward sleep tonight, imagine the invisible biological passengers traveling through the atmosphere above you, some serving as the seeds around which raindrops form, others swept into existing droplets and carried back to Earth, all participating in the vast circulation of living matter through air, water, and land that makes Earth not just a planet with life on it, but a living world where biology influences even atmospheric processes and weather patterns. Fall to Earth, physics of descent. Follow now the raindrop's journey from cloud to ground, discovering how gravity pulls it downward while air resistance shapes its form, how terminal velocity limits its speed, how evaporation may shrink it during descent, and how the physics of falling water drops reveals fundamental principles of fluid dynamics and aerodynamics that apply to objects ranging from microscopic particles to spacecraft re-entering Earth's atmosphere. When a raindrop first separates from a cloud and begins falling, gravity accelerates it downward at 9.8 meters per second squared, the same acceleration that affects all objects in Earth's gravitational field. But unlike objects falling in a vacuum, the raindrop immediately encounters air resistance that opposes its downward motion, creating a drag force that increases as the drop's speed increases. The drag force depends on several factors: the drop's cross-sectional area, its shape, the density of air, and most importantly, the square of its velocity. This means that as the raindrop accelerates downward, drag force increases more rapidly than the gravitational force remains constant, until eventually the two forces balance and the drop stops accelerating, reaching what physicists call terminal velocity, the maximum speed at which it falls through the atmosphere. For small raindrops, around 1 millimeter in diameter, terminal velocity is only about 4 meters per second, roughly 9 miles per hour. A gentle speed that explains why light drizzle falling on your skin feels soft and harmless. Medium raindrops, around 3 millimeters, reach terminal velocities near 9 meters per second, 20 miles per hour, falling fast enough to make distinct splashing sounds when striking pavement or puddles. The largest, stable raindrops, about 5 millimeters in diameter, fall at approximately 9 meters per second before becoming unstable and breaking apart. The shape of falling raindrops changes with size, due to the balance between surface tension, which tries to maintain a spherical form, and air resistance, which flattens the bottom of the drop. Small drops remain spherical because surface tension dominates. Medium drops become slightly flattened on the bottom, like a hamburger bun. Large drops develop concave bottoms as air pressure creates a small dimple, and the very largest drops become so deformed that they break apart into multiple smaller drops. This breakup of large drops establishes an upper limit on raindrop size around 5 to 6 millimeters in diameter. Drops that grow larger than this in clouds become unstable during their fall and fragment into several smaller, more stable drops. This natural size limit explains why raindrops have a relatively narrow size range, despite the wide variety of cloud conditions that produce them. As a raindrop falls through varying atmospheric conditions, its trajectory is not perfectly vertical. Light winds deflect its path, creating the slanting rain you see during windy storms. The drop may tumble and rotate as it falls, especially if it has an irregular shape or internal variations in density. This rotation affects how air flows around the drop and can influence the rate at which it falls and evaporates. Evaporation during descent can significantly affect small drops, particularly when they fall through dry air layers. As water molecules at the drop's surface escape into the surrounding air, the drop shrinks, sometimes disappearing completely before reaching the ground, a phenomenon called virga, visible as rain streaks beneath clouds that fade before touching Earth's surface. Larger drops are less affected by evaporation because their volume to surface area ratio is higher, giving them more water content relative to their evaporating surface. The temperature difference between the raindrop and the surrounding air also affects its fall. Cool rain falling through warm air may evaporate more quickly, while warm rain falling through cool air maintains its mass better. This evaporative cooling of air by falling rain creates downdrafts in thunderstorms, where large amounts of rain evaporating in dry air cool the air mass, making it denser and causing it to sink rapidly toward the ground as a cool, potentially damaging wind. The sound of rain results from the impact of millions of drops striking surfaces, with pitch and volume determined by drop size and impact velocity. Light rain creates a gentle patter from small drops falling slowly. Heavy rain produces a louder roar from larger drops striking surfaces at higher speeds. The distinctive sound of rain on different surfaces, leaves, pavement, metal roofs, water, results from how those surfaces absorb or reflect the impact energy and vibrate in response to the collision. When raindrops strike water surfaces, like puddles, ponds, or oceans, they create characteristic splash patterns determined by the drop's size and velocity. The impact creates a crater that rebounds, sometimes ejecting a small jet of water upward that can break into tiny droplets that re-enter the atmosphere, a process that contributes to the transfer of gases and particles between water bodies and the atmosphere. The impact of raindrops on soil has profound effects on erosion and soil structure. The kinetic energy of falling drops can dislodge soil particles, beginning the erosion process. On bare soil, heavy rain can compact surface layers, reducing water infiltration and increasing runoff. Vegetation intercepts raindrops, reducing their impact energy and protecting soil from erosion. One reason why deforestation increases erosion rates and why agricultural practices that maintain plant cover help preserve soil. As you rest peacefully tonight, while rain might be falling somewhere on Earth, imagine each drop descending through the atmosphere, reaching terminal velocity within seconds of leaving the cloud, maintaining its shape through the balance of surface tension and air resistance, occasionally evaporating partially in dry air layers, and finally striking the ground where it contributes to the accumulation of water that sustains life, shapes landscapes, and continues the eternal water cycle that connects atmosphere, land, ocean, and every living thing. Connections and cycles. The raindrop's place in Earth's systems. Contemplate now the raindrop as more than just a falling sphere of water, but as a participant in vast planetary cycles, a connector between atmosphere and land, a deliverer of dissolved nutrients and minerals, a sculptor of landscapes, a provider of the fresh water that makes terrestrial life possible, and a tiny but essential component in the climate system that regulates Earth's temperature and makes our planet habitable. Every raindrop that falls to Earth represents one stage in the water cycle, the continuous circulation of water between ocean, atmosphere, and land that moves approximately 505,000 cubic kilometers of water through the atmosphere each year. This cycle, powered by solar energy that evaporates surface water and by gravity that returns it as precipitation, has been operating since Earth cooled enough for liquid water to exist, recycling the same water molecules through countless forms over billions of years. The water in tonight's raindrops has been cycling through Earth's systems for as long as our planet has had oceans. Some water molecules have been locked in ice for thousands of years, released only recently by glacial melting. Others have traveled through the bodies of countless organisms, from bacteria to blue whales, participating in the biochemistry of life before returning to the abiotic world. Still others have been chemically bound in minerals deep underground, released by volcanic activity or weathering, and only now returning to the active water cycle. Raindrops deliver dissolved nutrients and minerals to terrestrial ecosystems in a process sometimes called wet deposition. Nitrogen compounds, sulfur compounds, calcium, sodium, and trace minerals dissolved in rain or attached to aerosol particles washed out by rain can fertilize soils and provide essential nutrients to plants. In remote ecosystems far from oceans, rainwater may be the primary source of certain nutrients like sodium, making precipitation not just a water source, but a nutrient delivery system. The chemistry of rainwater influences soil pH and mineral availability to plants. In regions where air pollution adds sulfur and nitrogen compounds to rain, creating acid rain, this affects soil chemistry and can damage sensitive ecosystems. In contrast, regions with clean air receive rain that is only slightly acidic from dissolved carbon dioxide, maintaining more neutral conditions that support diverse plant communities. Raindrops serve as primary agents of erosion, collectively transporting enormous quantities of sediment from highlands to lowlands, and eventually to the oceans. The energy of falling raindrops dislodges soil particles, while accumulated rainwater creates runoff that carries sediment downslope. Over geological time, this rain-driven erosion shapes landscapes, carves valleys, creates drainage patterns, and delivers nutrients and minerals from continents to the sea, influencing ocean chemistry and providing nutrients that support marine life. The spatial and temporal patterns of rainfall determine which ecosystems exist in different regions. Tropical rainforests exist where rain falls abundantly and consistently. Deserts occur where rain is scarce. Seasonal patterns of rainfall create Mediterranean climates, monsoon systems, and the distinct wet and dry seasons that characterize savannas and tropical grasslands. The character of ecosystems, the distribution of species, and the structure of food webs all reflect local precipitation patterns established by the physics and chemistry of raindrop formation and distribution. Rainwater infiltrating into soil replenishes groundwater aquifers that store vast quantities of fresh water underground. This groundwater provides drinking water for billions of people, sustains rivers during dry periods through base flow, and maintains wetlands and springs that serve as crucial habitats. The rate of groundwater recharge depends on precipitation patterns, soil characteristics, vegetation cover, and human land use, all factors influenced by or influencing the raindrops that fall on a landscape. Climate change is altering precipitation patterns globally, changing where, when, and how much rain falls in ways that will reshape ecosystems, agriculture, and human societies. Some regions are becoming wetter, with more intense rainfall events, while others are experiencing reduced precipitation and longer droughts. Understanding these changes requires studying not just large-scale atmospheric patterns, but also the microscopic physics of how raindrops form, grow, and fall, demonstrating that small-scale processes matter for planetary scale changes. The isotopic composition of rainwater, the ratio of heavy to light isotopes of hydrogen and oxygen, provides climate scientists with tools for reconstructing past climates. Ice cores from glaciers preserve layers of ancient snow, with each layer's isotopic composition revealing the temperature at the time of precipitation. By analyzing these isotopic signatures in ice layers stretching back hundreds of thousands of years, scientists reconstruct past temperatures and precipitation patterns, revealing how Earth's climate has changed over time and providing context for current climate change. As you drift peacefully into sleep tonight, rest in the knowledge that the simple raindrop connects you to planetary processes operating at every scale from molecular to global. The water falling as rain tonight has traveled through oceans and clouds, through soil and streams, through plants and animals, through ice and vapor, connecting all of Earth's systems in an integrated cycle that makes our planet unique in the solar system. A world where liquid water exists at the surface, where this water continuously circulates between Earth and sky, and where this circulation creates the conditions that allow life to thrive. Sleep well knowing that you live on a water world, where raindrops falling from clouds represent not just precipitation, but the continued operation of the planetary systems that regulate temperature, distribute nutrients, shape landscapes, replenish freshwater resources, and maintain the hydrological cycle that has sustained life for billions of years, and will continue as long as our planet retains its oceans, atmosphere, and the solar energy that drives evaporation and creates the clouds from which raindrops fall. Sweet dreams under the protection of Earth's water cycle, where every raindrop tells a story of journeys through multiple states of matter, multiple ecosystems, multiple systems, from microscopic to planetary, all connected through the simple elegance of H2O, the molecule that makes Earth habitable, that constitutes most of your body, and that will continue cycling through the systems that sustain life long after tonight's rain has fallen, soaked into soil, joined streams, and begun the next phase of its eternal journey through the water world we call home. As consciousness fades into dreams, rain may be falling somewhere on Earth, drops forming in clouds, descending through atmosphere, carrying dissolved gases and living organisms, sculpted by physics into their characteristic shapes, striking surfaces with energy that shapes landscapes and sustains life, each drop a tiny universe participating in the grand cycles that make our planet living, dynamic, and beautifully, intricately connected across all scales of matter and time.